Hello once again. This time around, we're going to take a look at exponential functions. They are, we're back into the world of like families of functions, elementary functions that we use as the kind of basis for all more, more complicated functions that we encounter after this. So exponential functions are just kind of considered an elementary foundational function that we need to, family of functions that we need to be familiar with. So um, exponential functions themselves, well, they're not linear, they're not rational, um, which are the two, we've kind of been paying attention to. Um, they're not polynomial functions. They're not degree 2, degree 4, degree. They're not polynomial functions at all. They're their own separate family of functions. So let's kind of introduce you to a data set where an exponential function would be more appropriate. So let's look at this data set here. We have mobile data growth throughout the world, starting back in 2010, looking at the years 2010 to 2014, so a 4-year span. So if you look closely, we've got these data points, right? We've got this data that was collected showing the total monthly data usage in petabytes, which is a lot bigger than a gigabyte. And then where we're at in the year. So quarter 1, 2010, quarter 2, 2010. So 4 times a year, kind of checked in to see just how much mobile data was being used worldwide. So we've got these data points that I've kind of highlighted here. And again, a linear model, well, I mean, you could argue a linear model would be best here. Maybe the line of best fit looks like that. But again, by using a linear model, you're saying that the rate at which mobile data use throughout the world increased was constant. That's what a linear function does for us. It shows a constant rate of change. But in this case, it probably was not constant. It looks like as the years went on from 2010 to 2014, yeah, the mobile data usage increased, but it didn't increase at a constant rate. Instead, it looks like it's a little bit more like this shape here. We go from 300 petabytes. Not sure how to say that word, so if I'm saying it wrong, forgive me. We go from 300 petabytes in fourth quarter 2010, and that just about doubles by fourth quarter in 2011. So it doubled in about a year's time. And then to double again, 2012, so about a year later, it doubled again. So it looks like every year it's doubling. Well, that's not a constant rate of change. You're not increasing by a particular fixed value. You're increasing by a percentage. You're doubling. So when you increase by a percentage, that's a different kind of growth. That's exponential growth. So if you just kind of focus on like here, and then when it doubles, about right here, then when does that double? Doubles right here. So you get a doubling. You get an increase by a certain percentage, 100% increase. That'd be doubling. Every year, it looks like, according to this data. So that's not linear growth. That's something else called exponential growth. So exponential growth is great at modeling situations where a value increases or decreases by a certain percentage on a fixed unit of time. So in this case, once a year, it looks like it doubles. About, right? Everything's approximate. This is experimental data. So we have a need for a new type of function. And we've given that function a name. It's called an exponential function. So as always, we want to start with a definition. So an exponential function is going to be any function of the form f of x or y equals c a to the x, where c is a real valued constant, and a is a real valued constant. Except for a, we're going to define it to be positive and not equal to 1. So we're going to need a to be positive and not equal to 1. Now the reason we want to define it to be positive will be a lot more clear later when we look at the next elementary function that's connected to this. But for now, we want the base of our exponent. So the exponent is x. So the independent variable is the exponent, exponential function, exponent. It's the first part of that word right there, right? Exponent, right here. That's where the independent variable is, right there in the exponent. The dependent variable is y, or f of x, or whatever name you want to give your function. So c is just a constant. C could be any number except 0. I guess we don't want c to be 0, so never mind. So I guess let's go back and adjust that. We don't want c to be 0. Because if c was 0, 0 times anything is 0, then you're back to having a horizontal line, which is a polynomial function. So we don't want c to be 0. Should have said that earlier. I apologize. Now, looking at this function, let's see if we can't figure out its domain. So the only arithmetic here is we're taking a positive number, raising it to a power, where x is the power. X is the exponent. Well, as we learned in Algebra 1 and Algebra 2, exponents can be negative, exponents can be positive, exponents can be rational numbers, exponents can be irrational numbers. So it turns out, since x is the exponent, and that's the only arithmetic involved, is taking a positive number to that power, x can be any real number. So the domain is all real numbers. That's not going to be true for the range, though. The range, well, if a is positive, a positive number to the power, to any power, is never going to be negative. Is never going to be negative. So if c is positive, this will always be positive, so the y value will always be positive. But if c is negative, then a positive number times a negative is a negative. So depending on what c is, that'll change the range. Okay, so why don't we write it this way? So if c is positive, then our range, y will be positive. If c is negative, then the output will be negative, because a negative times a positive, right? This is because a to the x is always positive. If I take a positive number to any power, it always comes back positive. Okay, so c kind of controls our range. Now, as always, we're going to want to focus on parent functions first, because then we can apply transformations to those. But we want to focus on parent functions. So some exponential functions, they're not in this form originally, and we have to rewrite them to be in that form. So like down here's an example. Let's say we have g of x is 2 to the negative x. Well, that's not the form we want, right? It's supposed to be, it's supposed to just be 2 to the x, and we have 2 to the negative x. Well, it turns out that's actually an exponential function because you can write 2 to the negative x as 2 to the negative 1 times x. And then using our exponent rules from Algebra 1, 2 to the negative 1 times x is equal to 2 to the negative 1 all raised to the x. And 2 to the negative 1 is 1/2. So it's actually 1/2 to the x. So this is just giving you an example of, let's say you have an exponential function 2 to the negative x, and you go, wait, that's not an exponential function. I've got this negative 1 up here. Ah, it is an exponential function because you can rewrite this as 1/2 to the x. So there's your a. A is equal to 1/2, and then it's raised to the x. So it is an exponential function. So it's just a quick reminder that we can use exponent rules to rewrite a function to be in the form that we want it to be in. Okay, so with that in mind, let's turn our attention to parent functions. What is the basic shape of an exponential function, and then we can apply transformations to those to get different versions. So let's take a look at a couple different parent functions. Let's look at the base being 2, and let's look at the base being 4. So let's start with this first one where the base is 2. So we've got f of x is equal to 2 to the x. Now 2 to the x is the same thing as 1 plus 1 to the x. Now why does that matter? Because this 1, adding 1 to 1, that's 100% increase. So back in Algebra 2, we talked about appreciation and depreciation, and we did exponential functions back in second year algebra, but we looked at them briefly. We'll look at them a little bit more closely this time. But you might recall that, if you have y equals 1.2 to the x, that's the same thing as 1 plus 0.2 to the x. So that's a 20% increase. That's a function that always applies a 20% increase every movement of 1 unit down the x-axis. So since the base is 2, and the way I arrive at 2 is doing 1 plus 1, right? You want this to always be a 1. So it's always 1 plus something or 1 minus something here, as we'll see in a second. But that's a 100% increase. Well, let's see what that looks like when we graph it. So let's make a quick t-chart just to kind of get a feel for the shape here. The arithmetic's not bad. Remember, the domain is all real numbers, so I can pick things like, negative 3. 2 to the negative 3, that's 1/8. Or I could pick things like negative 1 and get 1/2. Or I could pick 0. 2 to the 0 is 1. 2 to the first is 2. 2 squared is 4. 2 cubed is 8. So these numbers get big real quick. Like if I do 2 to the 4th, I'm already at 16. Or if I do 2 to the 5th, I'm already at 32. Right? So it's always 100% increase, or it doubles, right? So the output doubles. So you can see that, right? It doubles. 1/8 plus 1/8 is 2/8. Oh, wait, that's not fair. I went from negative 3 to negative 1. I jumped a little bit, didn't I? So let's try that again. So right here to here, that doubles. 0 to 1, that should double. 1 to 2, that should double, right? So 1 times 2 is 2. 2 times 2 is 4. So every time I increase by 1 on the x-axis, this doubles. So if you add 1, this doubles. If you add 1 to x, the output doubles. So if we plot those, let's see what that looks like. So we got to do quite a few tick marks here. Let's see. So I'm going to go by, well, let's see. That might be all right. That might be okay. We'll go by ones. So I think that goes all the way up to 20. And I don't think we'll need to go more than 5, because an exponent of 5 is pretty large. Start to get some pretty big numbers. We'll go down to -5. 2 to the -5th is a pretty small number. So let's plot some of these. So -3, 1/8, -1, 1/2, 0, 1, 1, 2, 2, 4, 3, 8, 4, 16, so 20, 19, 18, 17, 16, something like that maybe. So 2 to any power will never be 0, so it's never going to touch the axis. So we can see that we have a horizontal asymptote, because no matter what I plug in for x, I'm never going to get 0. Even if I plug in something like -50, 2 to the -50th is not 0. It's really tiny, but it's not 0. So this thing's never going to touch y = 0. So that's a horizontal asymptote. Okay. So this is an increasing function. This is an increasing function. And what's happening is every 1 unit of increase on x causes the output to double. So if you add 1 to x, then the output, which is f of x, doubles. That's what's happening for this function. But more importantly, it's the shape we're after. This is the shape of a parent function. This is one of our parent functions, y = 2 to the x. 2 is the base. But let's do another one here. Let's do this y = 4 to the x. Let's do that one. So if g of x is 4 to the x, that's the same thing as doing 1 plus 3, which means we're going to get a 300% increase. So the output is going to increase 300% every time x gets bigger by 1. So if you don't believe me, let's try it. So there's x and g of x. So if I plug in something like -3, 4 to the -3, that's 1/64. That's really tiny. -2, that's 1/16. -1, that's 1/4. 0 is 1. 1 is 4. 2 is 16. 3 is 64, I think. So notice every time x gets bigger by 1, it's a 300% increase. So that'd be what, times 4? Multiplied by 4, if I'm doing that right. Which makes sense. We know that's how exponents work. The base is 4, you're multiplying by 4 each time. Whereas like over here, you just add 1 to get to the next. So what we should see when we graph this is we should see the same shape, but it should be much steeper because the y value is getting bigger much, much faster. Much faster. So let's find out. So like -1, 1/4, 0, 1, 1/4, 2/16. So yeah, this thing is much steeper. Same shape though, kind of the same shape, but much steeper. So again, these are two parent functions. Notice that the base was bigger than 1, so we had a % increase in the output. And the further away it is from 1, the bigger that % increase is and the steeper the function is. It's never vertical though, by the way. These functions are never vertical. The domain truly is all real numbers. You can plug in any x and you'll get an output. Well, what if instead of adding a number to 1, you subtract a number from 1? What would happen in that case? So what if we had 1/2 to the x? Well, that'd be the same thing as doing 1 minus 0.5. So that means we have a 50% decrease. So my output's going to decrease by 50% every time x gets bigger by 1. So again, we can see that in the arithmetic. Let's try it. If I plug in -3, 1/2 to the -3 is 8. Then I go to 4. Then I go to 2. Then I go to 1. Then I go to 1/2. Then we go to 1/4. 1/8. So half. So I'm decreasing by 50%. So look, if I start at 8, 50% of 8 is 4. So I'm decreased. So I lose 4 and go down to 4. 50% of 4, though, is 2. So I'm losing 2. 50% of 2 is 1. I'm losing 1. So it's a 50% decrease. You can see that right here in the numbers. I've got a base of 1/2, though. So you're basically going to multiply by 1/2. Which is the same thing as a 50% decrease. So every time I add 1 to x, I get a 50% decrease, or I multiply the output by the previous output by 1/2. So again, the arithmetic, makes sense with what we're seeing up here as our base. So what is that shape going to look like? Well, let's go see. So I'm going to go out 5 either way because those are some pretty big exponents. I'll go up to 16 tick marks, see if I can fit everything on there. So 1, 2, 3, 4, 5, 6, 7, 8, -3, -2, 4, -1, 2, 0, 1, 1, 1/2. So it's going to look like this. So it's the same shape, but flipped over the y-axis, which we can see that right here. So you're going to flip the graph of y equals 2 to the x over the vertical axis. Right, that's one of our transformations. If I replace x with -x, I flip it over the y-axis. And that's exactly what happened. I have that same shape that used to look like this, right? This is what the shape used to look like. There's y equals 2 to the x. But I replaced x with -x, so it flipped it over the y-axis. So we get this decrease. This is a decreasing function. This is a decreasing function. Right, it's a 50% decrease specifically. So I don't know if we need to do a t-chart for this one, right? You guys kind of get the idea now that if I have 4 to the -x, that's 1/4 to the x. So that's a number that's even closer to 0, so my decrease should be even more dramatic. So I'm basically multiplying by 1/4 each time. So for example, if I were to plug in, say, -1, I'm automatically at 4. I'd be already here. Then 0, 1, then 1, 1/4. So it's going to be, again, a lot steeper, but never vertical. A lot steeper, but never vertical. But notice it has the same horizontal asymptote because you still can't get 0 as your output. That's not possible. That's not possible. So 1/4 to any power is never 0. 1/2 to any power is never 0. So again, this is a couple examples of some parent functions here. The difference is, though, these bases were numbers less than 1. they were less than 1, right? You took 1 and subtracted a positive number from it. 1 minus a half is a half. So you get this, you get a number that's a positive number. Remember, the base has to be positive, but it's less than 1. You get this decreasing function. So we call that exponential decay. So now let's generalize this. Let's generalize it. So if you have y equals a to the x, so you've got y equals 1 times a to the x. If a is bigger than 1, so you're taking 1 and adding a number to it, this is exponential growth. This is exponential growth. So your graph is going to be an increasing function with the shape that we just saw. Right? It's going to look like this. And the only coordinate that's guaranteed is this one right here, which is 0, 1. Because any number to the 0 power is 1. So this is a parent function. This is a parent function. Make sure that's clear. This is a parent function. So we can transform these. We can apply transformations. This is a parent function. So some of its key properties are that it's always increasing. Its domain is all real numbers. Its range are all the positive numbers. It's got a horizontal asymptote at 0. Goes through 0, 1 is the y-intercept. But most importantly for us is its shape. It's that shape that we care about. Now, as we saw, we could have decay. We could have exponential decay. We could have a decreasing function. And that's this right here. So if the base is between 0 and 1, so it's a fraction less than 1, but positive fraction less than 1, again, this is a parent function. This is going to be one of our parent functions, and this is exponential decay. So this is where we get this shape, right? So it decreases rapidly. Guaranteed to go through 0, 1, because, well, any positive number, the 0 power outputs 1. So our properties, a lot of the same properties, except for this one's always decreasing. But a lot of the other stuff is the same. It still has a domain of all real numbers. It still has a range of all the positive numbers. Y equals 0 is still the horizontal asymptote. Zero, 1 is still the y-intercept. But again, what's important here is these are parent functions. So I can flip these, shift them up, shift them down, shift them left, shift them right. We can do all our transformations. These are merely the parent functions. That's how all these elementary functions work, is we want to know what the parent function is, and then we can apply all our properties that apply to any function, all our transformations that apply to any function. So for example, let's say I wanted to graph this exponential function. Well, the first thing I would recognize is that the parent is y equals 3 to the x. The base is 3. The base is 3. So that's what my parent is y equals 3 to the x. This is exponential growth, right? It's 1 plus 2, so it's a 200% increase. 200% increase. So to graph with transformations, I need my parent function to start. So I'm going to have that be y1. I'm just going to get 5 good points. That's usually enough to get the shape. So I'm going to do like -2 to get 1/9. -1 would be 1/3. 0 would be 1. 1 would be 3, and 2 would be 9. You can pick in any 5x values that you want, but I don't want to use a calculator, so I'm going to pick those. And then I'm going to apply my transformations. So I've got a shift left and a shift down. So it doesn't matter what order I apply those in, thankfully. So I'm going to go ahead and do the shift left. So I'm going to subtract 2 from x. So subtract 2 and get -4, subtract 2, subtract 2, subtract 2, subtract 2. But my outputs stay the same. And then my final transformation is to shift everything down 4 units. And that'll give me my final function. So everything's going to get shifted down, including my horizontal asymptote. So down 4, down 4, down 4, down 4, down 4. Again, I'm plotting points here, so I don't need precision. Whatever 1/9 minus 4 is, I don't need a perfect value for that, because when I go to graph it, it's not going to be perfect anyway. But you can get a decimal if you want. It's fine. Grab a calculator, get a decimal. It's cool. No big deal. But notice my horizontal asymptote has changed. So right here, y equals -4 is the horizontal asymptote. Because it was y equals 0, but I just shifted everything down. I just shifted it all down 4. So I'm going to go put that on there first. Then I'm going to go plot my points. 0, 5, -1, -1, -2, -3, -3, really close to -4, -4, even closer. Again, I mean, I was never going to be perfect with those anyway. So here's my shape that we recognized from earlier. Notice it's been transformed though. So it doesn't go through 0, 1 because I shifted everything. Everything got shifted. So transformations were applied, so the horizontal asymptote changed, and so did the y-intercept. But the shape is the same. It's exponential growth. It's exponential growth. But there she is. Okay, next up, we need to remind ourselves of another very important irrational number. Pi is usually square root of 2, or pi is kind of the first irrational number that people are introduced to. But then a little bit later, we introduce you to this number e. E. So it's a lowercase italicized letter e, and that is a number. It's a very important and famous number in mathematics. And it turns out e, just like pi, is approximately 3.14159, so on and so forth. E is approximately 2.71828. Your calculator will tell you that. Your calculator has an E button on it. So just ask your calculator what e to the first is. And if you don't know how, just ask me. I'll show you how to use it. But it's a very important number with lots of definitions. There's actually lots of ways to define the number e. And in class, I would love to go through a few of those definitions. Whereas like pi, right, there's kind of one big way that we define pi and introduce it to younger persons, and that is, with a circle, right? We say when you have a circle, area is pi r squared, circumference is 2 pi r. So pi is really the circumference divided by 2 times the radius, or circumference divided by the diameter. So the circumference of any circle divided by its diameter is always equal to pi. That's kind of the first main way to define pi. And then later on, we found other ways to define pi. E is a very similar thing where there's lots of ways to define it. None of them are the perfect one that just where if you define it a particular way, it just makes sense to everyone because E just shows up in so many different um, applications and situations that there's just lots of ways you could define it. So I've given you one way in the definition, or I'm sorry, one way in these notes. So one way to define E is to say that E is the number that is approached as larger and larger values of n are plugged into this expression. So for example, if you plug in 1, you get 1 plus 1 to the first is 2. So that output is 2. But what if I plug in a bigger value? So what if I were to plug in, say, 50? Well, if you plug in 50, you get a few of these decimals. If you were, and you can check this on a calculator. If you were to plug in, say, 1,000 for n, you'd get some more of these decimals. So the bigger and bigger number that you plug in for n, integers, although I don't know if that matters, but definitely if you plug in bigger and bigger values, if you plug in 1,000,000, 1,000,000,000,000, 1,billion, you get more and more digits of E. It starts to give you more and more of these digits. So the larger that n is, the closer you get to E. And that idea is called a limit. You'll learn about that in calculus here pretty soon. But again, that's just one way to define E. There are others. There are other ways you could approach a definition for E, but that's one way. And again, in class, I'm happy to go into more detail and some other definitions and talk about why it's important. For now, I'm just kind of reminding us that we have this number. Notice that it's positive. Also notice that it's bigger than 1. So notice that E is positive and bigger than 1. So E is positive and bigger than 1. So it's exponential growth if it's the base of an exponential function. So the natural exponential function is, so this would be a parent function, right? To be a parent function would be y equals e to the x, where e is approximately 2.71828. So it's exponential growth. It's exponential growth. It is a percent increase, but that gets a little bit more complicated because you have to approximate that percent. It's about 171.8% increase, so it gets a little bit more complicated to word it, but it is a percent increase. It's exponential growth. So let's see an application where the base E is used. So it turns out in statistics and probability, we have different models that model the probability of certain situations. And one of those models uses exponential functions of base E. This is not a prob stat course. I'm not going to go into any more detail than that, but when you do take that course, or a course that involves some statistics and probability, where you go into a little bit more into detail, you'll see there are probability distributions that are modeled by exponential functions that are base E. So, for example, between 9 p.m. and 10 p.m., cars arrive at a particular fast food establishment's drive-through at the rate of 12 cars per hour, which is about 0.2 cars per minute. The following gives the probability, so this is important, the following gives the probability that a car will arrive within t minutes of 9 p.m. So for example, let's say I plug in 1 to this. Let's say I plug in 1, all right? So then let's evaluate that. 1 minus e to that power. So using a calculator, we get about 0.1813 if we round. So what is that telling me? This is telling me that there is an 18.13% chance a car will arrive within 1 minute of 9 p.m. So I guess another way to think of it is there's an 18.13% chance a car will show up in the drive-through between 9 and 9:01. is another way to think of that. So by plugging in t, you're finding out the probability that a car will arrive within that many minutes of 9. So just to do one more, let's say you plug in 12. So now you're going to plug in 12. So it'd be 1 minus e to the negative 0.2 times 12 power. Again, use a calculator. Let's see what we get. We get 0.9093. So again, that's telling me that there is an, or a, am I correct grammar here? 90.93% chance a car will arrive within 12 minutes of 9 p.m. So basically, pretty good chance you're going to get a car sometime between 9 and 9:12 in the evening. All right, so what's it ask us to do? It says determine the probability that a car will arrive within 5 minutes. Then do it again for 30. What happens as t increases? Well, we just did 1 minute and 12 minutes, so let's go do 5 and 30. I'm not going to, you guys saw me plug one in up here, so I'm not going to write that down again. But again, just use a calculator, no big deal. It's fine to use a calculator here. So if you do 5 minutes, you get about 0.6321. And if you do 30 minutes, you get about 0.9975, which makes sense, right? So the longer you wait, the more likelihood you're going to get a car in your drive-through. It says what happens to the probability as t increases. So as t increases, the probability approaches 1 or 100%. So if you wait long enough, you're going to get a car. There's a 100% chance you're going to get a car. So the longer you wait, the closer, the higher the probability is a car is going to show up. So that's just one example where you can use where the base of E is used to tell us something important about the world around us. Not the only example at all. Matter of fact, an argument can be made that in early mathematics, exponential functions are some of the most applicable. Linear functions definitely are in the running for that, and so are exponential functions. They're just used for so many different situations. Appreciation of object, the value of an object, depreciation of the value of an object. So like the housing market, cars, collectibles. We just saw probability, interest, savings accounts with interest and retirement accounts with interest and credit card interest and interest for a loan. I mean, there's just so many situations. Population growth, the population growth of our state, our town, our city, our world. There's just so many applications for percent increase, percent decrease, which is modeled by exponential functions. This was just one such example.